Okay, good afternoon, everyone. I hope you're all well. I'm going to start I think the presentation's already started here. And the recording started, so I'll start the presentation. So today we're going to talk about manufacturing process modeling with DEFORM, and this is number 2 in a series of webinars. This one we're going to focus on hot forging. I'm going to give an overview of the system, introduce wild PDS vision, talk about why we use simulation, discuss the DEFORM system and the hot forming modules. We'll talk about some application examples for hot forging, cogging, extrusion, and rolling. There'll be a demonstration of the software capability by Thomas, and hopefully some Q&A at the end. So if you've got any questions, then feel free to ask those. This is the second in the series. We gave an overview a couple of weeks ago, overview of DEFORM. We'll focus today on hot forging applications, and then in subsequent webinars we'll talk about cold forming, heat treatment, machining, joining, and other applications. During the webinar today, participants are going to be muted, but you can put your hand up if you want to ask a question, and we'll record that, and then we'll try and answer them at the end. The session's going to be recorded, so you'll be able to look back at that, and we'll make presentations available at the end if people want them. About wild analysis. Wild analysis was since end of last year. We're part of a larger group now called PDS Vision, which is a Scandinavian-based, well, global-based company now, founded in 2008 in Stockholm, and they operate in 10 markets. It's a digital transformation company specializing in 3D design, CAD, PLM, product data management, and CAE. And Wild Analysis are the experts within the group on the CAE. Wild Analysis have been distributor for DEFORM for over 20 years, and we cover Northern Europe, so UK, Scandinavia, Benelux, and France, and Ireland for tech support, software sales, and training. So if you have any interest in those applications, then you can contact us and we can discuss that. Besides DEFORM, we also cover codes like Reliasoft for reliability analysis, ANSYS for many types of different simulation, computational fluid dynamics, and finite element analysis. Moldex 3D is injection molding applications, and we also cover some geotechnical modeling through Bentley. And wider through the PDS Vision group, we cover a lot of other applications, but we're not going to talk about those today. If you're here at the last webinar, we talked about the product and process development and why it's important to start using simulation for these kind of applications. For hot forging design specifically, it's been around for a very long time, and design and development's traditionally been based on trial and error and experience, but the luxury of having spare capacity in workshops these days is it's a luxury that doesn't exist much anymore. So stopping production, taking on trials is a big challenge for people. So expertise in developing new processes can take years to develop, or decades, with these traditional processes, and sometimes these production processes can be acceptable rather than optimized. And developing a new process, the time to market can be slow for challenging parts or new materials or aggressive processes. So in today's market, these old methods really are a bit non-competitive. So simulation really can help by providing design feedback much earlier on in the process. So if you look at a new process development, the cost of that trial really ramps up. You do the initial engineering, you cut some tools, you do some trials, and you don't get any feedback until right at the end when you start inspecting the part and looking at how it's performed. But you can use simulation up front in that design process, go through the manufacturing process design, get really early feedback in there so that when you do go to shop trial on your production process, you'll have a lot more confidence that you're going to get it right first time, or be able to drill down to that good production process and get it up and running really quickly. So that's the overall vision of why simulations, one of the many benefits of simulation, but in terms of upfront process design. And it really gives you an option to try out these virtual trial runs prior to cutting any tools or forming any parts, so that you can try and understand how the material's flowing, where the material's going to move, what the loads are on the tooling, whether the tooling can withstand that, what kind of tooling design you need, and the material specs that you'll need for those tools as well. So you can run these tryouts on the computer. You'll be able to look inside the part, see how the material is going to flow, show hidden behavior that you might not see, such as flow defects, and get that early feedback to try and help you improve the design or narrow down your design. And that will hopefully lead you to have much more successful shop floor trials. The software we're looking at today is DEFORM. It's an integrated manufacturing process modeling system, and we cover a whole gamut of processes, right from the edge of casting. We don't really model casting per se. There's some very good codes out there, Procast and other kind of Magmasoft and things like that, but we can take the results from there into DEFORM and start from there for hot forging applications. And today we're going to cover these primary processing applications like cogging, forging, rolling, extrusion, and discuss some of those, give some examples, and most of the other things that we cover we'll talk about in other webinars. But if you have any interest in other applications, you can contact us and we can discuss that. DEFORM itself provides a multi-physics simulation environment. So on a base level, in the top part of this inverted triangle, we're looking at thermomechanical processing. So I heat up some metal and I deform it, and the material will flow based on its temperature, and we'll develop some stress and some strain depending on how fast you deform it, i.e. the strain rate. We can also add on a microstructure capability to look at phase transformation in steels, and or look at grain growth and recrystallization kind of applications. And in terms of heating your part up, we can look at that either through sort of furnace modeling, or induction heating, or resistance heating applications. And what we're really interested in understanding the flow of the material by evaluating the flow stress at the various throughout the process as the strain evolves for different strain and strain rates and different temperatures. And that's the crux of what we're trying to solve in DEFORM. In terms of predictive capabilities, the kind of things that typical customers are looking to get out of the simulation is, does it fill the die cavity? Do we get a good fill? Is it going to meet the tolerances that we require for the part, and perhaps the machining tolerances for the final component? So non-fill or underfill. Also, you want to understand in more complex forming applications whether you're going to get gas or lubrication traps, so that I can vent the dies should I need to do that. Again, in many processes, understanding whether you're going to get folds or laps or other defects, the flow-through defects, is going to be quite important, so that you can design the preforms or get the right billet size, or understand the positioning and the processing for the operators, if you're using that, or the feed systems. Of course, forming load is very important, so optimizing the temperature and thermal cycles to get an understanding of the load throughout the process and the various progressions of your process is very important. And of course, you may have a range of different machines, so depending on what kind of press you're looking at, whether you're looking at a hydraulic press or a screw press or a hammer type press or other rotary applications, then you can design the process based on what equipment you've got. In a lot of places, we're looking at damage and fracture as well. Is quite important to understand how the material is going to perform. And then obviously taking care of your tools is quite important, so understanding die deflection and fracture and failure in the tooling is essential for a lot of applications. And as people move to high strength materials and forming those, this becomes more of a challenge, and die design is critical in these applications. And that includes wear as well, die wear, thermal cycling, etc. Typical user applications for DEFORM, covering those processes from die fill down to microstructure. The software can cover all of these applications, but we need to decide on how we train people to understand the tools and how they're going to be applied. For basic simulations like die fill, lapse, flash prediction, and load prediction, we have a set of entry-level tools which are used typically by designers and engineers who are just looking at that process design and understanding how the material's flowing. But when we get to the other set of the scale, we've got, when we're looking at metallurgy, things like microstructure, grain size, recrystallization. The onus is really on the end user to understand what's going on with the recrystallization kinetics and understand the metallurgy, and we provide a set of tools which are easy to use to apply your knowledge to understand the process. So from a hot forming perspective, we start in our entry-level system with Forming Express, either 2D or 3D, 2D for axisymmetric parts and 3D for three-dimensional parts. And then as we increase the feature set and capabilities as we go up to DEFORM 2D and 3D. And with 2D and 3D, we also have these hot forming application modules. So forming, shape rolling, cogging, extrusion, ring rolling, and there's also the design of experiments which can tag onto that as well. So we're going to cover some of these applications and modules and give a demonstration. So typically, the most common one used by DEFORM users is forming. This is the default module that you'll get, and it's typically modeling some thermomechanical process with multiple operations, looking at material flow, die fill, and forming loads. On the primary processing side, we're looking at applications like cogging or open die forging, which is applicable to GFM kind of applications as well. Where you're going through many sequences of forging simulations, and setting these up manually would be very challenging. So we have an automatic system to do this, which we'll talk about in a bit. Then we have tied, sort of sits in between the forming and cogging sort of templates, really. We have a multi-blow template, which can be used for multi-blow hammer screw press processes. So where you've got using the same set of tools, and you're using an energy-based system to control the energy that's going into the part through multiple blow sequences. So this would be typical for turbine disc applications, or in this case, this is a gear blank for a hammer forged gear blank. Another common hot forging process, which follows on after the sort of cogging application, would be extrusion, and we'll talk about the options we've got available in DEFORM for that. So there's sometimes it's done cold with, but also a lot of aluminium hot forging. Oh, this one's still running. A quite complex application, often done hot, ring rolling. Again, we have a separate module for that, which is dedicated for, it's quite a specialist process, and we'll talk about that in a bit. And then the final one, shape rolling, where we're going to give Thomas is going to give a demonstration of this and talk about that in a bit more detail. So the most basic module, or the most common module used in DEFORM, is the forming module. Here's an example of a hot forged yoke, where typically a user might be looking at billet size, length, and position to understand what the optimum forming process is. In this case, there's 3 components forged in a single die with a single hit. So on the left, you can see the setup in DEFORM, the multiple operation system, where we'd have a heat transfer first, which would be taking it out of the furnace at a certain temperature, and it's going to be transferred onto the tools for a forming operation. So they're testing out 3 billet sizes here. So they first tested out a large diameter bar, and we get good fill in the process here. So you can look at the contact and the fill in the die, great fill, but there's a lot of flash in there. So there's going to be a lot of scrap. So it's not an optimum process. So perhaps we need to look at a smaller bar. So if you go to a smaller diameter bar, then we get quite good fill in here, but the flash is marginal on the vertical parts of that. And also the fill on the middle component is not ideal. So that would mean when you start looking at a bit of, some tolerancing size on the bar coming in, then you might get some scrap rates out of that. So positioning with a nominal size bar in this case is quite good, and it's a bit shorter, but in this case that bar size, due to the backfill at the end, causes a lap in one of the components. So again, in this one it's not an ideal process. So using the same bar but with a slightly different positioning system, we get a good fill with reasonable flash and no defects. So we've evaluated bar size and positioning on that one, and that's a very typical process, and the final component looks like this. So simple process, single blow, but you can look at various operations to look at those characteristics, looking at fill, whether I get laps, defects, and you can optimize the positioning. So you can then design the tooling so that you can get the positioning right consistently. So that's a typical kind of process. Going on to rolling applications, DEFORM's used in quite a lot of areas for these kind of solutions. In DEFORM 2D, we can do plane strain kind of analysis for 2D plate and sheet rolling. We have a special 2.5D solver, and we'll talk about that in a minute, for shapes and progressions and looking at shape evolution. And for that one, we use the shape rolling template with the DEFORM 2D solver. We have a 3D Lagrangian and 3D ALE processes for looking at steady state and rolling progressions, continuous ones, again in the shape rolling template. But for general rolling applications, such as the cross wedge rolling example here at the bottom, where I've just got normal tools, you can just run these kind of things in general DEFORM 3D using effectively the forming template as well. And with those more general applications like DEFORM 3D, we can do rolling with multiple deforming bodies as well. So in this case, we have a pack rolling, so we have a multi-material. So we're using an interstitial material around a canning process around the end to thermally protect the inner part which we're rolling. In the shape rolling module itself, we've got two options really. We've got a 3D Lagrangian, and generally DEFORM is an implicit Lagrangian solution for most of the applications we're looking at. It's a very mature solution. It's been used for decades. And we can do transient and steady state predictions and handle very complex geometries. And what the template allows you to do is set up many sequences of these processes to either look at multiple passes, reversal rolling, blooming kind of applications, or very long components as well. And the ALE, on the other hand, is a faster solution to look at those steady state processes. It's set up all via a wizard, and it can utilize the 2.5D results to construct a starting shape. It can handle more complex sections than the 2.5D, which we're going to talk about in just a sec. And the 2.5D, so 2.5D simulation, the reason it's 2.5D because during rolling, if you took a cross section at the roll, you'd see the cross-sectional area changes during that process as you take the section. So we get flow in and out of the screen. So we have Thomas will explain how that works in just a minute. So we got the SFTC developed this unique solution for DEFORM, which allows you to set up a simulation very quickly and it's very good for relatively simple shapes, flats, oval, rounds, but you can do more complex shapes in that. And you can run many iterations in just a few minutes and get feedback on the shape, the torque, separating forces, and the state variables for the processes. So I'm going to pass over to Thomas now, who's going to give a demonstration of the forming, roll forming application.
Good afternoon, everyone. I've got a recording of a demonstration prepared, which I'll just share now. This demonstration is of the DEFORM shape rolling operation. This specialized template greatly simplifies the setup of multiple rolling passes and also has some specialized solver features for rolling. We will go through the process of setting up a series of roll passes and running this in a quick 2.5D simulation before using this 2D model data to automatically generate 3D geometry and meshes of the workpiece and rolls for a 3D ALE steady-state simulation. We first start by creating a new DEFORM project. In this case, we're going to call it rolling demonstration and make sure we're on SI units. Then we add a shape rolling operation from the Operation Explorer. This consists of a rolling group which is used to batch set up all the roll passes. Working from top to bottom through the tree, we will enter all the data needed for the model to be created. We'll be looking at a quarter symmetry model, and we're going to assume the tooling is a constant temperature. Next, we define the cross-section of the workpiece and set its initial temperature. We will model this as a rigid viscoplastic object, neglecting small elastic strains. Next, the geometry of the cross-section is imported from CAD. For the mesh, given the deformation this will go through over 19 passes, we will up the cross-section element count to 300. 2D meshing is very quick. Next, we set the workpiece material. In this case, we will select a steel from the DEFORM material library. Note how the velocity and convective heat loss boundary conditions for the object are automatically set on the symmetry planes because we've defined quarter symmetry previously. The groove list is where we define the cross-section geometry for all the different roll passes. We have 19 passes, but only 6 roll grooves to define. Once we have all the roll grooves defined, we can move to the pass table. Here we can quickly define key parameters for the pass, including the groove, roll RPM, and roll gap. Once we define the first pass, we can add a second to the table, and so on. Note, as we add passes, an operation tile is generated for each pass. Once we have finished setting up all the passes, we can proceed to run the 2.5D simulation. This took about 10 minutes to run through 19 passes. We can look at the predicted strain and temperature after each pass. Here, strain is selected as the state variable, and the graphics window updates with the strain plot at the end of each pass. You can zoom in to look at the strain development progression through each pass. Key results are summarized in a rolling results table, which we can copy into Excel. We can also open this sub-simulation in the DEFORM post-processor and can animate the development of the shape simulated at sections through the roll pass. Each step of this simulation is a slab cross-section through the workpiece as it goes through the rolls. The 2.5D simulation works under the assumption that there is no out-of-plane strain or any heat transfer out of plane. It's useful to look at the 2.5D results using this post-processor because you can see the development of contact. This gives quick feedback on the design of the roll geometry. Again, we can plot the temperature of the workpiece to see how much it's cooled down during the process as it loses heat to the environment and to the rolls. So we close the post-processor and the 2.5D results. The next step is to go to the 3D setup. And here you can see DEFORM has automatically created geometry for the 3D rolls and a 3D mesh for the workpiece. For the case of an ALE simulation, this can actually use the 2.5D simulation results as a better initial guess for this simulation. We can fine-tune the mesh here to add more or less layers in specific zones. The final step is to set the simulation controls. This looks at the simulation time stepping and convergence criteria. By clicking Apply to all passes, we apply those settings to every single pass within the rolling group. You can see that each operation has 3D geometry already generated for each roll. The workpiece geometry will transfer from each roll pass to the next, with the updated shape carried forward. So this concludes the rolling demonstration. In summary, I've shown how DEFORM has bespoke operation templates that expedite the development of models of complex process chains. In this case, setup of a 19-pass rolling schedule can be done rapidly, initial results extracted within minutes, and further 3D simulations set up automatically using the 2D data. DEFORM has a series of other operation templates which have targeted workflows, for example, multi-blow forging, open die cogging, and extrusion. Okay, James, back to you.
Okay, thanks, Thomas. So on that note, just talking about multi-blow forging here. Here's a typical example of multi-blow forging, a handheld operation where, in this case, a high level of scrap, so 11%, was managed to get down to about 3.4% with cost savings of over $100,000 on the process for these. So the original process here on the top left was a 3-die operation, or 3-cavity operation here. So the first one was a roll with 5 blows, followed by a blocker with 4 blows, and then a finisher on 1 blow. So the way that that's set up in DEFORM is we have initial heat transfer, and then we have this blow table, which is a multiple blow operation. In this case, it's a hammer forging. And once you set up that single instance of simulation in there, you have a blow table which allows you to set the energy per blow in there, and we can also define what the lift is on the die, and whether we rotate the part during those operations as well. So it sits in between the cogging and a forming template, really. So we can have a sequence of these. So in this original operation on the top, you can see we'd have a 5-blow operation, and then a 4-blow blocker, and then the heat transfer in between the two, and then a finisher operation. And the modified process below, we just do 2 light blows on the first one, so you would reduce the energy on that particular operation. Then move on to a preform, which had 4 blows, a blocker with 3 blows, a heat transfer, and then a finish. So the system allows you to try out different scenarios for these processes, looking at different energies to optimize the process. So the original process looks like this. There's the initial blow there. And then the final blow. And the modified sequence looks like this. So just that initial light one to get it to fit into the main preform. So a much more robust and consistent operation to reduce the scrap. So subtle changes to make a big difference in the overall process. So that's the multi-blow template. The other one Thomas mentioned at the end was ring rolling, which is a very specialized process, which consists of localized deformations, very small contact regions, and there's rigid body motion that's going on. Often there's multiple rolls and supporting guide rolls or potential multiple deformation rolls. And these processes are prone to ring instability. From a numerical perspective, these can take a long time to run. So it's been a challenge for many years to run these. So DEFORM have developed a specialized solver to look at this. And I'll just show you an example here. So here's one with some guide rolls on there, some axial rolls, and they control the axial, prevent the axial growth in the ring and control the overall height of the ring in that region. So we've got a specially developed finite element engine for this ring rolling process, which is a couple between a Lagrangian and ALE type process. It has a local Lagrangian solution and an ALE updating in the circumferential direction. There's a dedicated wizard in here to set up the processes, and it's post-processed with the DEFORM. What's special about ring rolling is that all the deformation happens in a very localized area. So if you look at the picture on the left, that shows the strain rate of the material. So you can see on the right hand side of that left image, there's the area between the drive roll and the mandrel has a small area of deformation, and the area between the axial rolls has a small area of deformation. So all the deformation growth is happening in those small areas, and the rest of it is not doing much, really. It's behaving as a elastic ring effectively. So DEFORM decouples the simulation up into different regions and different zones. We use a structured brick mesh that's rotated around the ring here, and DEFORM automatically targets that mesh size to maintain a good level of contact during the process in those deformation zones. So you get roll contact between the mandrel and the drive roll, and you see the two axial rolls. You can see the contact nodes in there. So it's very fine areas of contact. So these things could become quite unstable. So DEFORM determines where the strain rate area is going on, and it decouples the simulation into multiple zones. So in the bottom image, you can see the 4 zones. We've got 2 Lagrangian deformation zones, which are calculated using DEFORM, the standard Lagrangian solution. But we use an ALE updating circumferentially in this one. And then the white regions are consolidated into specialized super elements, so they can behave essentially like beams and twist and deform elastically in there. And then we have an updating algorithm to allow the nodes to follow the curvature of the dies as well to help with the solution accuracy. So that's one solution. And I think the final operation template we'll just briefly discuss is the cogging open die forging template. So as the animation showed earlier, we go through many operations along the length of the bar. So all the data is input in a table here to allow you to define a very hundreds or if not thousands of operations, which are sequences of small deformations and cooling down between the bites as well, to look at the consolidation of porosity, refine the grain structure, and create the desired shape from the end of the process. And a typical application of that might be, in this case, this is an example of titanium cogging. So we're showing the grain size evolution in this example here. We start off with a very coarse microstructure, and it's broken down into fine grain structure to give you the desired thermomechanical properties, the mechanical properties that you'll need to deliver, which can be used later on for manufacturing specific components. And this might go on afterwards to be rolled or extruded or just forged into a different shape. one more application which is to cover, and that's extrusion. So in DEFORM we have a dedicated extrusion template, which is we have 3 solutions for that. We use a standard updated Lagrange solution, which is similar to a forging, but we're just pushing this through a die cavity here, and we're looking to understand the load stroke and the breakout load of this. Also understand the weld zones and how the material comes back on itself. We can also solve this with a one-step analysis using steady state to determine that, but we don't capture any transient effects with that. And then something that sits in between where we can capture the transient is the ALE solution, which is slightly different. So Lagrangian, we push it through, and we're looking at, there's lots of remeshing in the solution there. Where we start off with the initial mesh of the billet, simple mesh of the billet, and the mesh evolves during the process, and we refine the mesh as it gets through to the extrusion dies, and we're tracking the force during that process on the load stroke. So that's the force on the tools and on the RAM as well, so that we can understand the whole process. When we get to applications like steady state and ALE, we don't update the mesh, so we create one static mesh for the whole process, so we assume it's already extruded, and then we split it into different zones, and mathematically we solve these in different solutions using an updating algorithm on this. And the ALE and the steady state mesh will be the same kind of, exactly the same mesh, but with the slightly different numerical solution. And once we get these out, we can start looking at die stress on the tooling, and that's quite an important objective in this. So we'll mesh the tools, we'll map the forces over from the Lagrangian process or the ALE process, and then we can run a simulation on the die stress to look at the full. We can then start looking at the die stack deformation in the die stack and the supporting tools, and do the stress analysis to look at the stresses in there and evaluate potential for cracking and high stresses. So that is a whirlwind overview of the hot forging capabilities within DEFORM. Are there any questions that we have on any of the topics we covered today? Okay, so Alric has a question, I think. Okay, can we unmute Alric? Hi, Alric. I've unmuted you. If you can talk, or you can type.
Hi, James.
Hi, Alric.
Can you hear me?
Yes, I can hear you.
Okay. Yeah. Thanks. Thanks a lot for the presentation. It's great to see all the application and and updates. Just a question regarding the cogging.
Yeah.
I just wanted to know if in the version 13 there was some improvement compared to version 11 or 12, respectively. I mean, in respect to the, can you set the reference plane, as you do the cogging process, the bar elongates, but sometime for the location of the bar, in the model, can you set maybe the end plane as a reference, or the cold, or like the gripper end as a reference? Now I know that was an issue maybe in previous version.
Thomas, didn't we looked at that last recently, didn't we? I think.
Yeah, I believe that's been addressed.
Yeah.
I know they've made some changes to the offsets and
and the reference points.
tools.
So
also
you can either your reference points can either be absolute or relative to the bar itself.
Okay,
So
that's
I think
great.
you can set by default, because when you start the process of the cogging, you don't know, you kind of don't know where it's going to be at the end of that first pass. It really
Yes.
depends on the deformation and that, so you don't know the absolute distance. But if you were programming it, so if you were trying to make a digital twin, for example, which is probably where you're coming from, then you can use absolute distances.
Okay, no, that's great. And maybe another question, I mean, because we are thinking to combine, you know, the all the modeling we did on the furnace with the cogging or open die forging operation. Does that take into account, you know, the gripper? Can you model, you know, like the heat transfer or heat loss, you know, when
Yeah,
is
you just, so yeah, in this cogging, so yeah, so in this process here,
yeah,
so you could have, you did the cogging just be one operation. So when you pass the billet through, the billet's just a component that you're passing through in a multiple operation. So you could have a thermal, or you could have a normal forming operation, or whatever you want, and then pass it to cogging. So that
okay,
forming operation just could be a heat transfer, which would include the grippers for there, so you can calculate the thermal, you know, changes due to the handling of the bar. Yeah.
okay, no, thank you.
Yeah. But you don't, you just need to do a thermal simulation for that. It's relatively relatively easy to do.
Okay.
Just to add one recent improvement with the cogging module is you can now program in a section, so that when the billet gets long enough, it can be sectioned, and more cogging passes continue.
Yeah.
Okay.
Yeah.
Okay,
So
no,
if you
thanks.
take, yeah, so if you took your billet out, I mean, for your, I know the press that you were talking about, but so I don't think that'll be an issue for you. But for when you get into really longer parts, they normally section it and then split the bar into two and then process the two parts separately. So.
Okay, yeah, I don't think we would do that. But yeah, no, that's interesting to hear. Okay, no problem. Thank you very much.
Thank you. If there are any other questions, if you want some more updates for those that are on there that are already DEFORM users, there's the DEFORM user group next week, which if you haven't got the invite for, please drop me an email and let me know, and so you can register for that. And that's the two sessions with SFTC, when that's going to look at what the current developments are with DEFORM for I guess 13.01, which is just coming out now, and what the future developments are for the capabilities of the software.
When's the next webinar, James? That we're
Oh
running?
yeah, sorry, thank you, Thomas. The next webinar is going to be cold forming on the 19th of May. We'll talk about cold forming applications and I think die stress and shrink fits and the like. So okay, well, thank you everybody for attending, and I hope you have a good rest of the week, and hope to see you at the next webinar.
Thank you, everyone.